Hello, I'm going to go ahead and show you some applications of Ampere's law. I'll start off with the simple cases, but I'll show you the gory details of what's really going on. I'll use polar coordinates just because that makes life a little easier to see exactly what's going on. So anyways, let's get started. And then after I do a simple case, then I'll do a more complex case, sort of a worst case scenario. Let me try to get this in focus now. Okay, so Ampere's law says that the closed integral of b dot dl, in other words, this is a path integral and it goes around a closed circle. It has to be a closed shape anyways, and it is a path integral. But according to Ampere's law, that's equal to mu 0 times I enclosed. And again, mu 0 is 4 pi times 10 to the negative 7th. And I advised you before that that's Tesla meters per ampere. So that's the units. So I'm going to show you how to actually apply this. This is a weird thing again where we're going to basically solve for the integran of the equation. Now the Ampere's law is Ampere's law. It's not Ampere's helpful hint that sometimes works. It's Ampere's law. But if you're using it to compute the magnetic field, it's only in certain symmetries that it works. If you want to use it, say, to calculate the current enclosed, that always works. It's in principle so with the other way, except it's really hard to pull an integran and a dot product out of a integral to find out the magnetic field. So let's start off with a polar coordinate system. So I'm going to say this is my x-axis coming out of the page. This is my y-axis going parallel to the page. And this is my z-axis. And of course, you know we have a I hat vector that points in the positive x direction along the x-axis. It's 1 unit long, exactly 1 unit, not 1 meter, not 1 kilogram, exactly 1. There's a j hat vector pointing along the y direction, and then there's a k hat direction pointing along the k direction, or k hat vector pointing along the z direction. What I'm going to do now is draw a wire. And I'm going to assume this is an infinitely long wire, so we won't have any fringing effects, if you will, of the actual magnetic field. So it goes on forever and ever. Now, according to Ampere's law, we can choose any closed loop, and whatever, as long as we calculate what current's going through that closed loop, that will allow us to figure out the integral of b dot dl. So what I'm going to do is, I realized from the right-hand rule and what we did with the law of Biot-Savart that if this was a wire and I grabbed it with my right hand with my thumb pointing in the direction of current, like that, then the magnetic field would coil around in a counterclockwise direction. So I'm going to be smart and choose an Amperian loop whose center is the center of the circle of the wire. And it is, in fact, another circle. Of course, it looks like an oval because I'm trying to draw it in 3 dimensions, but it should be a circle of radius r, say. Now, in order for me to do a line integral, I actually got to evaluate the b and the dl along the line. I'm going to hypothesize, based on my learnings from the law of Biot-Savart, that the magnetic field B is only dependent on R. This infinitely long wire should make it not dependent on Z or even on theta, which would be the angle swept out from the positive x-axis around. So I'm just going to call it B of R, to letting you know that it may or may not depend on R, but I'm certain it's not going to depend on theta, which is another one of the cylindrical, or in this case cylindrical, but if you're in 2 dimensions, you call it polar coordinates. And I'm going to say its direction is actually in the same direction as theta increases. So it turns out there's actually a unit vector associated with theta, and it's called theta hat. So that's the actual direction of B. And then I'll say that dl is an infinitesimal vector dl, And its length would be, if I allow this to go from here to say here, this small angle right here would be d theta, and that arc length would be r d theta. So the length is r d theta, but it too points in the theta hat direction, which is wonderful because when I do a dot product, it's nice to have vectors that are parallel. So that's my hypothesis, is that B is only a function of R and that it always points in the theta hat direction. Now, if you look from above at the XY axis, let's say this is X and this is Y. I want to just show you what theta hat and all that good stuff is. So there's Y. So if we take an arbitrary point in space right here, the angle of theta that we're talking about is a counterclockwise angle measured from the positive x-axis. And then, of course, r in polar coordinates is the distance you are away from the origin. So if I wanted to actually imagine what the unit vectors would look like, I would say, okay, well, r is going to be radial. In other words, it always points from the origin towards the point. So it's got to be parallel to the line connecting the origin to the point. And then theta hat, of course, would be perpendicular to that, because what's the point of having unit vectors if they're not perpendicular to one another? I mean, that's the best case scenario if you can actually do it. So this one's going to be r hat, and this one's going to be theta hat. So just so you know what they are, it's not that big a deal. But in terms of this, I could draw the x-axis over here again. This is angle theta. I could draw the y-axis over here again. Since they're 90 degrees, I know this angle is also theta. So I think you can see from that that r hat would just be cosine theta I hat plus sine theta j hat. Now it would be technically 1 times cosine theta, but it's a unit vector, so the 1 don't need to be written, or doesn't need to be written. Similarly, it would be 1 times sine theta for this dimension, so I didn't write the 1 there either. If you look over here, you see that the y component of the y hat would actually be the cosine of theta. And the x component would actually be the negative of the sine of theta. Again, I'm using the fact that the hypotenuse of this triangle I'm imagining is 1. So from that, I can get that theta hat is in fact equal to negative sine theta I hat plus cosine theta j hat. So now that's physically what they are. And in fact, if you ever have to integrate or differentiate unit vectors and you have a theta hat or an r hat or any of the other coordinate systems, you generally have to reduce them back down to I hats and j hats because of this complex nature. You can't just integrate, because I is actually a constant vector and j is a constant vector, but you can see r actually depends heavily on position, as does the theta hat. So anyways, that's what those are, just for your knowledge. Now, what that means is I take the left-hand side of Ampere's law, which is the closed integral of b dot dl, and I compute that. And it looks horrible. It's an integral. It's got a circle on it, which we've never seen before. It's got a dot product, well, we have in Gauss's law. It's got a dot product in it. It's got vectors. It just seems horrible. But what you realize is it just turns out to be an integral of b of r theta hat dotted with r d theta theta hat. Again, the dot product is a linear operator, so I can take the magnitudes b of r and r d theta and pull them out in front and just let the theta hat dot theta hat happen on its own to figure out what the dot product is. But we know the dot product, a dot b, is just equal to the magnitude of a times the magnitude of b times the cosine of the angle between them. Well, these two are parallel, so the cosine of the angle between them is 0. Hence, cosine of 0 is 1, and the unit vectors, so they're unit vectors, so this is 1 and this is 1, so I just get 1 for the dot product. So I'm left now with the left-hand side just being equal to b of r. Notice the r is in there, but the integral is taken with respect to d theta, so I can pull the r and the b of r out in front. So I'll say b of r times r integral d theta, and I got to integrate this over the entire path, which I think you can tell is 2 pi radians. So it goes from theta equals 0 to 2 pi, and lo and behold, I'll get 2 pi r B of R for the left-hand side. Now, if you do everything correctly with Gauss's law, with Ampere's law, and you're trying to compute the magnetic field within the integral, you're always going to get, unless you did something horribly wrong, or you're trying to apply it to a problem that doesn't work, that it doesn't work for because it doesn't have the right symmetry. As long as it does have the right symmetry, you're always going to get some length times B of R. Maybe you'll have a couple different terms, stuff like that, but you don't have to go through this every time. You know what's going to happen. It's going to be, because we choose the Amperian loop in such a way that it's everywhere parallel to the magnetic field, or contrarily perpendicular to it, so it'll be zero. Because if it's perpendicular, the dot product's going to give you zero. But if it's parallel, not only is it not going to give you zero, it's going to give you exactly one for the dot product, and B is actually going to be a constant along that, so you can always pull that out in front. So that's sort of the whole nature of this Ampere's law. The left-hand side, though, the most complicated looking part, is almost always a very trivial little example of length times B of R, maybe length 1 times B of R, or B of L, or B of X, plus length 2 times B of R, B of L, or B of X. Anyways, that's it. That's what you have to remember every time you apply the left-hand side of Ampere's law. The right-hand side in this case is actually pretty easy too. So the right-hand side, I'll write right here, that's just Q enclosed, or excuse me, Q enclosed, that's mu 0 times I enclosed. Sorry about that. So the total current enclosed going through this loop, in other words, so you can sort of imagine a surface let's imagine this Amperian loop is in fact a ring of wire, and we stuck it in some mixture of glycerin and dishwashing soap, and we pulled it out, and it would make this little bubble, but it's just a flat bubble right now. But if you pulled it off this way or that way, it'd actually make a bubble. Otherwise, it's just a little flat plane. Well, when you say I enclose, you want to know what current is actually hitting or going through that bubble surface, if you will. So in this case, we know the current, I didn't even label it, but current is generally just going to be called I. And I'm going to say the I is going up because that's the direction I chose originally. I did say that, but I didn't write it down. So I know the right-hand side is just mu 0 times I. Now I set left-hand side equal to right-hand side, and that gives me 2 pi r times B of R is equal to mu 0 times I, which I think you can tell with my original hypothesis, B of R, or B is equal to B of R times theta hat. That gives me B is equal to mu 0 I over 2 pi R theta hat, which is exactly what we got from the law of Biot-Savart, and it's exactly the equation that you're used to working with. So again, I did not have to make use of all this stuff. I just gave it to you for transparency, so you wouldn't be afraid of the theta hat or afraid of the r hat. Just remember, the r hat's always pointing parallel to a vector from the origin to the point that you're talking about. The theta hat's always 9 degrees ahead, so you can use those just to indicate unit vectors rather than just make up one every time. Now, let's apply Ampere's law to a more complicated problem. I'm going to again put it along the z-axis just to make the mathematics work out sort of the same way. So this is my y-axis. This again is my x-axis. This again is my z-axis. And what I'm going to do is imagine a wire, and this wire is going to have a radius big R. Okay, that wire is essentially infinitely long, and all that really means in reality is you need to be closer to it. So for instance, if the wire is 10 meters long, you can get as close to about a meter from the center, and the equation should work really well. In other words, about 1/10 of the size, you need to be closer than that. And the closer you are, the more accurate it is. So I'm going to say this wire has a total current I coming out of it. But I know something else about the wire. I know that the wire has a very specific current density given as a function of R. J, the current density, which is really the differential rate of change of the current as a function of area, is actually equal to some constant A times R squared. Okay, so what that means is as I get further and further from the center of the wire, the current gets larger and larger, so that the vast majority of the current is flowing around the outside ring edge of the wire, and the inner part, the very center, has almost no current going through it. So that's just a typical type of way we can soup the problem up, and I'm choosing to do that. The question I will ask is, what is the strength of the magnetic field some distance, let's say R, away from the center of the wire? And what is the value of A? And maybe what are the units of the value A? Okay. So first off, let me attack the A so I can find out what that is. I do know that I, the current, is equal to the integral of J dot dA. Now, dA is a unit vector that basically points in the direction of the current, but it's perpendicular to the cross-sectional area. So if I again appeal to my cylindrical coordinates here, I could actually figure out what dA is. Now I see that J, which is what we're going to integrate, changes as a function of R. So I can't have a macroscopic change in R. I have to have an infinitesimal change in R. So I need something that's radially is quite thin, but it can be as big as it wants in the theta direction, the azimuthal angle direction if you want, and it can be as big as it wants, as big as I want in the K direction or the Z direction if I wanted. So what I will do is choose concentric rings, if you will, of thickness dr. Okay. Now the rings are centered. They're centered on the center of the axis of the wire, and of course the A vector points in the k hat direction. So with that in mind, I can say, well, dA, which is what this guy is, dA is going to be, it's basically a circle. So the length around here is 2 pi r, and then I just multiply it by dr, because if I cut that in half, it would look pretty much like this. In actuality, it'd look a little less like this than I'd really like to admit. It actually looks more like that, and that has that little tail on each end because this outer part has to be slightly bigger. But it turns out if you actually do the math and carry out the infinitesimals, that's a second order term. In other words, you get dr squared or dr cubed when you go to compute what this area actually is. So we're just going to treat it as 2 pi r times dr. So dA is 2 pi r dr. And of course, it points in the k hat direction. So I'll just put a k hat up there. Okay. So now I can integrate that. I get the integral of 2 pi r dr, and of course I put the j first because I messed up, and I mean the dA first, and the A or the j is A times r squared, and now I've gotten all the magnitudes out in front, and I'm just going to do k hat times k hat because that's the direction of the j as well. I didn't write that before, but I should have. So I get k hat dot k hat, and of course, just like we did before, k hat dot k hat is 1 times the cosine of 0, which is just 1. So now I can say, well, this is pretty straightforward. The 2 pi and the a come out in front, and I get the integral of r cubed dr, and I'm going to integrate that from r equals 0 to big R. Well, I think you can see what that's going to become. That'll be 2 pi a times r to the 4th over 4. And since I is something I'm supposed to know, what I really want to try to figure out is what is A. So A from this has to be, for starters, I get to cancel out this 2 and this 4 and leave a 2 on the bottom. So A is going to be 2 times I over pi, that's going to come down to the bottom, over r to the 4th. So now I think you can see what the units of A would be as well as what A is. So this is one part of the problem that I would actually call, say part A. What is the value of the little constant A in the expression for the current density? And it appears to have units of amperes per meter to the 4th. So that's another type of question I might ask you. Part B, what are the units of the A in the current density? But now that I have that, I can now leave everything in terms of I when I actually do solve a problem. So what we're going to do now is calculate the magnetic field both inside and out. So for R less than big R, the left-hand side of Ampere's law is going to become closed integral of B dot dl. I'm again going to make that same hypothesis. I'm going to say B is equal to B of R theta hat, and I'm going to say dl is equal to R d theta hat. And then, of course, the exact same thing's going to happen as happened up here. It's just going to become 2 pi r times B of R. So again, that's why I told you and explained to you that you're always going to get some length times B of R if you choose everything properly. So the right-hand side again turns out to be the left-hand side again turns out to be quite trivial. The right-hand side, again, we're dealing for R less than big R. The right-hand side is a little more complicated. It's mu 0 times I enclosed. I has the formula I equals the integral of j dot dA. So I'm going to say mu 0 times the integral of j, which is a r squared k hat dotted with 2 pi r dr, and that also is in the k hat direction. So this integral looks just like the integral we did here, except the range of integration is going to be from r equals 0 to r equals little r. Again, I get 2 pi a coming out in front. I get the integral of r to the 3 dr. I'm integrating from 0 to r, though, instead of 0 to big R. Oh, and I still got my mu 0, which will go right there. So I finally get mu 0 times exactly the same expression we got before, which is pi times a r to the 4th over 2. So I'm already canceling out the 2 and the 4 and changing the big R to the 4th down to the little r to the 4th. And I think I might have left off a good fraction of that right-hand sides when I was doing this because it slipped below the camera and I didn't realize it. So let me recap what I did. The right-hand side, the closed integral of b dot dl was identical to the integral we did up here. And it's identical more or less to what we're going to do every time with Ampere's law. We're trying to always find a symmetry that allows us to get a length times B of R. So I ended up getting 2 pi r times B of R. Then the right-hand side was the more complicated part. It's mu 0 times I enclosed. So mu 0 is written again. The I is equal to the integral of j dot dA. So j is a r squared k hat, and then I dot that with dA, which is 2 pi r dr in the k hat direction. Again, the a pi r, or excuse me, the a r squared, the 2 pi r, and the dr can just come out in front, and then I do k hat dot k hat, which is 1. So then I can integrate everything. The only thing that doesn't come out of the integral is the r cubed and the dr. So I get 2 pi a mu 0 integral from 0 to little r now of r cubed dr. And that result gives me the exact same thing I got up here, except instead of a big R, it's going to have a little r. So I got mu 0 pi a over 2 r to the 4th. But I really want it in terms of the current, so it can look like that mu 0 I over 2 pi r that we got before. So I'm going to substitute my value of a in there. So let's write it this way. I'll say mu 0 pi r to the 4th over 2. And now times a, which we found was 2i over pi big R to the 4th. So I think you can see what happens now. This pi is going to cancel out with that pi. This 2 is going to cancel out with this 2. And we ultimately have just mu 0 I r to the 4th over big R to the 4th. And that makes sense because the left-hand side should have units of mu 0 I, and R would have to be the same units for that to be the case. Now all I have to do is set the left-hand side equal to the right-hand side of Ampere's law, and I will have the solution. So setting the left-hand side equal to the right-hand side, the left-hand side was 2 pi r b of r. The left-hand side, excuse me, that's the left-hand side. The right-hand side is mu 0 I r to the fourth over r, big R to the fourth. And I think you can see now this r over here will cancel out and leave a 3 there. Let me write that a little better. It's going to cancel that out and leave a 3 there. So I can get b, which is equal to, according to our hypothesis, b of r theta hat should in fact be equal to mu 0 I over 2 pi big R to the fourth times r cubed theta hat. So that is the solution for r less than big R. So in other words, for r less than big R, it actually goes like r cubed. Now, if we did the same thing for r greater than big R, I think you can see we'd get exactly the same results. R greater than big R, we'd get the same results as we did for the regular wire, because all we know outside here is that current I is being carried through a wire. We don't know any of the details about J and all that. It doesn't matter. All we have is a current carrying wire. So for R greater than big R, we get B is equal to mu 0 I over 2 pi R in the theta hat direction. Again, this is for R greater than big R. Now notice if you actually let R equal big R, you'll get R cubed, big R canceling out with R to the fourth of little r, and you get just a single R in the bottom, which is exactly what you get here for R at R. So I can actually add the R less than or equal to big R. So that's the whole solution. That is the whole solution for a really big, ugly, usually scary calculus-based Ampere's law problem. I hope that helps you. Let's give you a chance again to look at all the equations just in case you missed something while I was writing. Had some students mention that sometimes they can't read my writing fast enough and it's a little pain to go back and forth, so I'm just going to put this right at the end and let you do that. You can pause it at any time. And when you pause it, you can then see any equations you might have missed or any of the work that I derived. So I hope that helps.